Hey guys, Miss Miklos here. I hope you are all having a great Friday morning. I'm sure I'm busy doing something up in Bishop, hopefully building something or helping somebody out somewhere. So in lieu of actually having me in class today, you guys get to watch this lovely video. So today we are talking about section 2.4, complex numbers. And everything we're actually talking about today is something that you guys have previously learned in Algebra 2. And that doesn't mean it's easy by any means, but today, hopefully seeing it a second time will be a good reminder for you. So, as we've seen in our previous lessons, many polynomials have imaginary zeros. And we saw that on our functions that did not cross the x-axis. We knew that that zero then was imaginary or not real. As a result, I just want to review complex numbers with you guys and how to work with them because we will have to deal with them the rest of this chapter. And the one thing I really want to stress to all of you is that imaginary zeros will always come in conjugate pairs. Okay, so that is a big deal, and I just want to remind us what a conjugate pair actually is. So if I had something like 1 plus I, the conjugate pair would be 1 minus I. So the key thing for us on that is that they are the same terms, just a different sign in between. So I'm writing same terms, different sign. So if we look at the standard form of what we call a complex number, we have a plus bi. And the whole purpose of a complex number is it is a way that we can write any number that has a real part and an imaginary part. So we can see a represents our real number, so we always put the real number first. And then we put bi, which represents our imaginary number, second. The other thing that I just quickly want to review is this chart that we can see on the left of your handout. And this chart, which I'm just going to circle right now, is just a reminder of what imaginary values actually are. Remember that I represents the square root of -1. And back in Algebra 2, you guys had to memorize all of these, and we dealt with them a lot. But the one that I really want to stress that comes up quite a bit is that I squared is equal to -1. Okay, so whenever I have an I that has an exponent greater than 1, we need to use this table to replace it with something that has a lower degree. And quite honestly, in pre-calculus, we definitely see this one the most often. Before we get into our examples, I also just want to remind you guys what these actual problems look like. And a lot of the times, we're just going to start off with something basic here. If we had the square root of -16, you guys learned last year that we should split this up like the square root of 16 times the square root of -1. I know that the square root of 16 is 4, and the square root of -1 is I. Now remember, we write this I kind of weird. It has like a little hook on the end, kind of like it's a backwards J, and the dot is a little bit bigger just to really let us know that we understand that this represents the square root of -1. So with that, we're actually going to get into some of our problems today. And sometimes on complex numbers, I think we overthink the problems. A lot of our problems today are going to be pretty simple as long as we treat I like a variable. So the directions for this set of our problems is telling us to write the answer in standard complex number form, which means that we're doing this a plus bi, so we have our real part first and our imaginary part second. So on number 1, we have the quantity 3 minus I plus the quantity 2 plus 3i. Whenever I have something like this, all they're asking us to do is combine all the like terms. So I'm going to combine 3 plus 2, which makes 5. -I plus 3i, I'm treating these like they're variables, and we know if we're adding variables together, all we do is combine their coefficients. So negative 1 plus 3 would give us plus 2i. This is our final answer. Okay, there's not much else we can do, and we notice this 5 represents our real part, and the 2i represents our imaginary part. Moving on to number 2, it looks a little bit more complicated, and the major reason why it's more complicated is because of this negative. And we know that whenever we see a negative out in front of a parenthesis, that means that I need to distribute. So the very first thing I'm going to do here is rewrite this as 3 plus 2 plus 3i plus negative 5 plus I. So if I'm adding all my like terms together, I notice 3, 2, and negative 5 are all constants, and when I combine those, they all cancel out and I end up with 0. Now 3i and I are also like terms, and when I add those together, I get 4i as my answer. So I just want to stress that just because we have imaginary numbers, it doesn't mean it's super complicated. We definitely have problems like 1 and 2 that you guys just need to take your time and use your algebra skills to figure out. If we take a look here at number 3 is a little bit different. Okay, the whole point here of number 3 is that we are multiplying two things together. So if I look, it looks like we are doing I times negative 3i. The reason why this is not distributing is because we know we can only use the distributive property when I have multiplication and addition. So this just means I'm multiplying all these things together. So I know my coefficient is negative 3, and I need to figure out what is I times I, and we've learned that when we multiply variables together, we have to add their exponents together. So I times I becomes I squared. Now just a side note, we said earlier if I ever have an exponent higher than 1, I need to replace it. We know that I squared is equal to negative 1. So I'm going to write negative 3 times, instead of I squared, I'm writing negative 1, which gives us an answer of 3. So I know often a lot of you guys think, okay, why do we have to learn these complex numbers? They're dumb. Why do we care about imaginary stuff? And this is kind of showing us that sometimes when we have imaginary values, our answer ends up being a real number. So that's why it really becomes important. And we'll see that also when we talk about writing equations given particular zeros. Number 4, we have another multiplication problem, and here, since I have a binomial times a binomial, I am going to use FOIL. So let me go ahead and just remind us that this is something that I would FOIL out. So 2 times 4 is 8. Outside 2 times 3i is 6i. My inside negative I times 4 is negative 4i. And lastly, negative I times 3i becomes negative 3i squared. So when I add all of my like terms together, I get 8 plus 2i minus 3i squared. Now once again, I have this I squared, which we know actually represents negative 1. So I'm going to think of this as 8 plus 2i minus 3 times negative 1, which would become 8 plus 2i plus 3, or 11 plus 2i. Now, as we get more familiar with I squared being negative 1, I definitely think we can skip some of these steps, but it's helpful just to see exactly where everything is coming from. Number 5 is another problem that we are foiling. However, before we do any work, I just want to make a special note on this particular problem that these are what we call conjugate pairs, and we talked about that vocab term at the beginning of this lesson. And the reason why that's going to become important is I want you guys to kind of see what happens to my answer. So I'm going to FOIL 3 times 3 is 9. 3 times negative 2i is negative 6i. 2i times 3 is positive 6i. 2i times negative 2i is negative 4i squared. So the first thing that I notice is that my I terms cancel out. Secondly, I know that I squared is the same thing as negative 1. So I'm saying 9 minus 4 times negative 1. So I get 9 plus 4, which is 13. So what I really want us to notice here is that when I multiply two conjugate pairs together, and just to review the reason why they are conjugate pairs, they have the same two terms, just the sign in between is different. When I multiply them together, we will always get a real number as our answer. Number 6 is another example of having a binomial. And I need to remember whenever I'm squaring something, that means I'm multiplying this binomial by itself. So the very first thing I'm going to do is rewrite this as 3 plus 2i times 3 plus 2i. And I would really encourage you guys to write this out because this is a concept I know you guys know how to FOIL. I don't want you to automatically make this 9 plus 4i squared because that is not correct. And this is the type of problem I really want you guys to get all the points on. So when I'm foiling this, 3 times 3 is 9. 3 times 2i is 6i. 2i times 3 is 6i. And 2i times 2i is 4i squared. Now, some things that we know, and I'm going to skip a step here. We know 4i squared is really equal to negative 4. And just to review how I'm getting that, I squared is negative 1. 4 times negative 1 is negative 4. So when I'm adding my like terms together, I'm going to do 9 minus 4, and I get 5. So that is the real portion of my complex number. Then I'm going to add together my imaginary numbers. So when I add those coefficients, I get 12i. So 5 plus 12i is our answer. Moving on to number 7. Some of you guys might look at this problem and think, oh, there's nothing we can do. Okay, we should just leave it like this. However, I'm putting a star by this problem because we definitely have a problem here. Okay, our problem is that I have this I in the denominator. And you guys have learned it is never okay to have a radical in our denominator. We know that I represents the square root of negative 1, so that means that I cannot have an I in our denominator at any point in time. A lot of times we can just multiply by I over I or something like that. However, this time I have a binomial. So what we're going to go ahead and do is multiply by the complex conjugate. So we learned a complex conjugate means I have the same two terms. We just change the sign in between. Since we have an expression here, I know that if I multiply by anything, I need to multiply by 1. So the way we can kind of get around this is I need to multiply the numerator and the denominator by the same thing. So I know in our complex conjugate we're going to have 1 and we're going to have I because those are these two terms. And I need to change this sign in between, so I'm going to put minus. So I'm multiplying the numerator and the denominator by 1 minus I. So in my numerator, when I multiply, 1 times 1 minus I is just 1 minus I. In the denominator, I'm going to FOIL those things together, and some of you might realize that we could take a shortcut. But when I FOIL, I would get 1 minus I plus I minus I squared. Okay, so I have 1 minus I in my numerator. In our denominator, these i's cancel each other out, and I know that negative I squared would be like negative 1. And we know when we subtract a negative, it's like adding. So 1 plus 1 would give me 2. Now, this particular problem right here is not written in our standard form. We know that we need to split up the real part and the imaginary part. So I'm going to write this as 1 over 2 minus, I could either write I over 2 or 1/2 I. Now, where I got this 1 from in front of, for the numerator for the 1/2 I, is that the coefficient here would be a 1. So key thing is when I have a binomial in the denominator that has an I in it, I need to multiply by the complex conjugate. So if we take a look at number 8, here's another problem where it looks like we have a binomial with an I or a square root, which we know that's really what it represents, down in our denominator. I also have 1 up in my numerator, but I want to stress it's okay to have an I in the numerator. We just can never have one down in the denominator. So I'm going to multiply by the complex conjugate. Now this time, I know our complex conjugate has a 4 and a 2i, and I need to change this sign in between, so it is going to be plus. Okay, there we go, a giant multiplication sign there. So now I'm going to FOIL the numerator, so I would get 8 plus 4i plus 12i plus 6i squared. In my denominator, when I FOIL, I get 16 plus 8i minus 8i minus 4i squared. And I know that I can simplify this further by adding all of our like terms together. Okay, in fact, we may remember 6i squared. We know that really means negative 6. 8 plus negative 6 gives us 2. When I add these two I terms together, I get plus 16i. In my denominator, I know negative 4i squared is like positive 4. 16 plus 4 becomes 20. And my I values cancel each other out. So I have 2 over 20 plus 16 over 20i. We've learned that we should always reduce our fractions. 2 over 20 is like 1/10. 16 over 20 is like 4/5 I. So this would be our answer. We have our real portion first, our imaginary portion second. Number 9 to me looks kind of frightening because we have like this radical 15 and then i's on the outside, and I have radical 3's. Okay, but I just want to show us that stuff like this really isn't that scary, especially because I noticed these are a complex conjugate pair. We know when we have a complex conjugate pair, our answer when we multiply them together should be a real number. So let's go through this. Radical 3 times radical 3 is 3. Radical 3 times negative radical 15i becomes minus the square root of 45i. And yes, we could simplify that further, but I'm going to wait until the end to do that. My inside terms, I get plus the square root of 45i. And then lastly, when I have radical 15i times negative radical 15i, I get minus 15, because that's radical 15 times radical 15. And then I times I is I squared. Now these two scary looking i's cancel out. So I have 3, and I know that negative 15i squared is the same as positive 15. So when I add these together, we get 18 as our final answer. So I just want to stress, even if these look super scary, when it's a conjugate pair, we will always get a real number as our answer. So the problems that we just went through, some of them were pretty intense, but we will have some questions that are this basic, and I would definitely expect to see something like this on a quiz or on our test, where all we need to do is just write the complex conjugate. So for A, we have negative 3 plus 5i. So I know that I have a negative 3 and a 5i. I just need to change the sign in between. So I would have negative 3 minus 5i. Okay, so even though we had a negative out in front, I kept that negative. All I'm doing in the middle is changing that sign in between. So my answer here, negative 3 minus 5i. Okay, second one, I have negative 7i, and this looks kind of strange because I don't have a real number added to it, but that actually makes it easier because it just becomes positive 7i. So if I just have, remember we call this a monomial, I only have one term, I know that it's just going to be the opposite value. Okay, so your homework tonight, you guys actually only have one assignment, and it is on everything that we just talked about. But what this is doing, it's actually leading us to a preview of our next section 2.5. And this is a little bit of a long lesson. It can be kind of time consuming. But once again, it's actually stuff we did last year in Algebra 2. What makes it kind of tough is that there's a lot of information that we're adding together. So I just want to preview it today, and then we're going to go into detail about this next time when I see you guys. So we are going to use synthetic division like we learned last class to find real zeros of the polynomials like the one below. So the question is going to say find all zeros, and I just want to make a quick note that when it says all, that means real and imaginary. And one thing that I want to notice is that when we have our graphing calculator, when I am graphing, the only thing that I can actually see are all the real zeros, okay, when we're using that zero function on our graphing calculator. We cannot see the imaginary zeros because they're not x-intercepts. So whenever it's asking us to find all zeros, I cannot just rely on my graphing calculator. So, just a few things. Remember, what do we look at to know how many zeros a polynomial will have? And we talked about this really briefly in class, but what we're going to look at is the degree. So in this case, if I'm looking at f of x equals x cubed minus x squared minus x minus 15, we're going to have 3 zeros in this particular case. So the way that we would set something like this up, I'm going to list out all the coefficients like we did in synthetic division. Remember, if we are missing a term, we would fill in a 0. What makes this one a little bit different is I don't quite know what my box number is, so we need to choose a box number. And the way we're going to do this, it is the factors of the constant divided by the factors of the leading coefficient. So if we look at this, I know that our constant is negative 15. So things that would multiply to be 15 would be 1 and 15. Notice I'm putting plus or minus because I could do positive 1 times negative 15, or I could do negative 1 times positive 15. We also could do 3 times 5. So those would all be in the numerator. Now we're going to divide by the factors of our leading coefficient. Our leading coefficient this time is just 1. So that would be the only factor. And I would write these out then as plus or minus 1, plus or minus 15, plus or minus 3, plus or minus 5. Okay, these really are the different options that we could use in our box. Now, at this point, I need to choose one of these 8 numbers, and we know probably 3 of them are going to work. And I'm going to put it in and use synthetic division. And I know that we are correct when I get 0 as a remainder. I always make a smiley face because it makes me happy because I don't have to work as much. Okay, and we're going to continue doing this until it is quadratic. And one thing we can do, if this is a section where we can use our graphing calculator, I might go ahead and graph this function and look and see, are any of these numbers x-intercepts? Okay, and that's something that can actually save me a lot of time to know what to put as our box number. So even if it's something where we have to do all this work, that's something that can definitely save us some time. So I actually graphed this in my graphing calculator, and I noticed only one x-intercept, which looked like it was at 3. So now I'm going to go through synthetic division. I'm bringing down my 1. 1 times 3 is 3. When I add down that column, I get 2. 2 times 3 is 6. When I add, I get 5. 5 times 3 is 15. And I get 0, which makes me very happy. So we learned earlier this week that I always write 1 degree lower than our original problem. Our original problem started with x cubed, so this is going to become 1x squared plus 2x plus 5 equals 0. Now I need to continue solving this, and this relates back to what we learned the very first lesson in this particular chapter. There are no factors of 5 that add up to be 2, so we can either complete the square or use quadratic formula, and it's really up to you. It doesn't matter. I'm going to use completing the square for fun. So I'm going to subtract 5. I know to figure out what to add here, I am taking that 2, and I'm going to divide by 2, and by 2 I mean this coefficient here. That's where this is coming from. 2 divided by 2 squared, which is 1. And I know whatever I add to one side, I have to add to the other side. When I factor this, it becomes x plus 1 squared equals -4. I'm going to then square root both sides, and when I square root over a number, I need to put plus or minus. So I get x plus 1 equals plus or minus the square root of -4 is 2i. So x equals -1 plus or minus 2i. These would be our other two zeros for this particular problem. So if you're looking at this going, oh my gosh, what the heck did she just do? Don't stress out. Okay, none of this is on your homework tonight. However, this is what we're going to be doing next class, so I just wanted us to kind of be aware of that. So the last thing I want to talk about on this is some vocab. Last year in Algebra 2, we really said choices for the box number, but we are really calling them possible rational zeros. And what that means is those are the only rational numbers that could possibly work. Okay, we learned back in Algebra 2 a rational number is any number we can write as a fraction of integers. So we're not putting in any imaginary numbers into the box, and we definitely could get imaginary numbers as our answers, but any possible rational zero that we're going to get is something that we are putting in as a possible box number. Okay, so just a reminder, this is how we find them, factors of the constant divided by the factors of the leading coefficient. It's really going to vary. Sometimes we will have a few choices and sometimes we will have a lot. Keep in mind that Mrs. Vaughn and I are kind-hearted people, and on our quizzes and tests, there won't be a ridiculous number of possibilities. On your homework, we are definitely going to be using our graphing calculator to help narrow stuff down. So that's a little preview of what we're doing next week. Make sure if you guys are struggling on anything, feel free to send me an email. Okay, and I will see you guys next week.